Hello everyone, I am Dr. Sirajul Faisi. I welcome you in my YouTube channel. Today we are going to learn molecular shapes. You know, Lewis structure give atomic connectivity. They tell us which atoms are physically connected to each other. The shape of molecule is determined by its bond length, angles. Consider carbon tetrachloride. Experimentally, we find all chlorine bond angles are 109.5 degrees. Therefore, the molecules cannot be planar. All chlorine atoms are located at the vertices of tetrahedron with the carbon at its center. You can see bond distance 1.78 angstrom, bond angle 109.5 degree. So, in order to predict molecular shape, we assume the valence electrons repel each other. Therefore, the molecule adopts whichever 3D geometry minimize this repulsion. So, you know one theory, we call this process valence shell electron pair repulsion theory. There are simple shapes for AB2 and AB3 molecule. You can see AB2 linear or bent, AB3 trigonal planar, trigonal pyramidal, and T-shaped. So, there are 5 fundamental geometries for molecule shape: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. So, when considering the geometry about the central atom, we consider all electrons, lone pairs and bonding pairs. When naming the molecular geometry, we focus only on the position of the atoms. You can see the tetrahedral, trigonal, pyramidal, and bent. So to determine the shape of molecules, we distinguish between lone pairs or non-bonding pair, those not in bond of electrons, and bonding pair, those found between two atoms. We define the electron domain geometry by the position in 3D space of all electrons pair, bonding or non-bonding. The electron adopt an arrangement in a space to minimize electron-electron repulsions. So friends, you can see number of electron domains 2, 3, 4. The arrangement of electrons domain linear, trigonal, planar, and tetrahedral. Electron domain geometry and predicted bond angles 180, 120, and 109.5 degrees. Now, number of electron domains 5, 6, arrangement of electrons domain, electron domain geometry, diagonal bipyramidal and octahedral, predicted bond angles 120 and 90 degree and octahedral 90 degree. So, Vsepr models. To determine the electron pair geometry, draw the Lewis structure, count the total number of electron pair around the central atom, arrange the electron pair in one of the above geometries to minimize electron-electron repulsion, and count multiple bond as one bonding pair. You can see you have the NH3 ammonia, Lewis structure, then electron domain geometry, tetrahedral, and then molecular geometry, trigonal pyramid. So, you can see the linear, you can see the trigonal planar, 3, non-bonding domain 0, trigonal planar. If you have the non-bonding domain 1, then bent. Example, NO2. You have the tetrahedral 4, 0, tetrahedral, 3, 1, trigonal pyramidal, and 2, 2, bent. water is the examples, ammonia is the trigonal pyramidal, and methane is tetrahedral. So, effect of bonding electrons and multiple bonds on bond angles. We determine the electron pair geometry only looking at the electrons. We name the molecular geometry by position of atoms. We ignore lone pair in the molecular geometry. All the atoms that obey the octet rule have tetrahedral electron pair geometries. So, by experiment, the HXH bond angles decreases on moving from carbon to nitrogen to oxygen. You can see 109.5 degree, 107 degree, 104.5 degree. Since electrons in bond are attracted by two nuclei, they do not repel as much as lone pair. Therefore, the bond angles decreases as the number of lone pairs increases. So, bonding electron pair nucleus and non-bonding pairs nucleus. So, see the situation. So, similarly, electrons in multiple bond repel more than electrons in single bond. So, you can see 111.4 in single bonds and 124.3 degree between double bond and single bond. So, atoms that have expanded octet have AB5 diagonal bipyramidal or AB6 octahedral electron pair geometry. For trigonal bipyramidal structure, there is a plane containing 3 electron pair. The 4th and 5th electron pair are located above and below this plane. For octahedral structure, there is a plane containing 4 electron pair. Similarly, the 5th and 6th electron pair are located above and below this plane. So, you can see trigonal bipyramidal 5-0 PCl5 trigonal bipyramidal 4-1 SF4 seesaw 3-2 ClF3 T-shaped and 2-3 XeF2 linear. In the same way, bonding domain 6, non-bonding domain 0, octahedral, example SF6. 5-1, this is a square pyramid, and 4-2, a square planar. So, to minimize electron-electron repulsion, lone pair are always placed in equatorial position. So, axial bond and equatorial bond. So, this is the geometry. In acetic acid, there are 3 central atoms. We assign the geometry about each central atom separately. You can see. So, when there is a difference in electronegativity between two atoms, then the bond between them is polar. It is possible for a molecule to contain polar bond but not be polar. For example, the bond dipoles in CO2 cancel each other because CO2 is linear. You can see in molecular shape and molecular polarity, bond dipoles 0, overall dipole moment 0 in case of carbon dioxide. In water, the molecule is not linear and bond dipoles do not cancel each other. Therefore, water is a polar molecule. You can see bond dipoles, overall dipole moment. The overall polarity of molecule depends on its molecular geometry. So, this is the examples of polar, non-polar, polar ammonia, and again polar methyl chloride and non-polar BF3. So friends, Lewis structure and Vsepr do not explain why a bond forms. How do we count for shape in terms of quantum mechanics? What are the orbitals that are involved in bonding? We use valence bond theory, bonds form when orbitals on atom overlap. There are two electrons of opposite spin in the orbital overlap. So I will discuss further valence bond theory in our next video. So I hope this video will be beneficial for you. If you like this video, then subscribe my channel and share it in your friend circle so that your friend also benefited with this video. So at last, at the end, I would say thank you.